You ever see two things happening at the same time and wonder, wait a minute, is one actually causing the other? Well, today we are going deep. We're going to unpack the science of how we tell the difference between a simple coincidence and a real true cause and effect relationship.
So let's start with a classic, kind of fun puzzle. Does eating ice cream make you more likely to get attacked by a shark? I know. It sounds completely ridiculous. But if you just glanced at the numbers, you might actually start to wonder. The connection looks surprisingly real.
And just look at this data. It's fascinating, right? When summer hits, ice cream sales just shoot through the roof. And at the exact same time, what else goes up? Yep, the number of shark attacks. It's a textbook correlation. But does one cause the other? Of course not. There's a hidden culprit here, a third factor, good old summer heat. Hot weather makes us want ice cream, and it also makes us want to go swimming in the ocean, which, is where the sharks live. This hidden factor has a name. It's called a confounding variable, and it is the #1 reason we get tripped up and mistake correlation for causation.
Okay, so how do actual scientists get past these tricky, misleading connections to find what's really going on? Well, they use this incredibly powerful way of thinking called causal inference. And really, it's just the science of asking, what if?
At its heart, causal inference is all about trying to peek into alternate realities. Think about it. To know if a new medicine really works, it's not enough to know what happens when you take it. The real question is, what would have happened to you, that exact same you, at that exact same time, if you hadn't taken it?
And this right here, this is the fundamental problem. We can only ever live in one reality. If you take that new drug and your headache goes away, great, that's what we see. But we can never ever know for sure what would have happened in the other reality where you didn't take it. That unobserved what-if world is what scientists call the counterfactual, and figuring out how to estimate it is the whole game.
The famous statistician Donald Rubin put it perfectly. He said, the fundamental problem of causal inference is that we can never observe the counterfactual. You just can't be in two universes at once. You can't both take the pill and not take the pill. So how on earth do researchers solve this impossible problem?
Well, they have an ace up their sleeve. It's one of the most powerful tools in all of science, the randomized controlled trial, or RCT. This is the absolute gold standard for finding causality because it's so cleverly designed to create a stand-in, a kind of statistical ghost of that counterfactual we can never see.
And the process itself is just beautiful in its simplicity. First, you get a big group of similar people together. Then, and this is the magic part, you use a coin flip, basically, to randomly divide them into two groups. One group gets the real deal, the actual treatment. The other group gets a placebo, a sugar pill that does nothing. And then at the end, you just compare the result.
That randomization, that is the secret sauce. Because you're assigning people by pure chance, you make sure that, on average, the two groups are pretty much identical. Same mix of ages, health habits, everything. The only real difference between them is that one group got the treatment and the other didn't. This means that the placebo group becomes an almost perfect stand-in for the counterfactual. It lets us isolate the true effect of the treatment and nothing else. It's genius.
But you can't always run an experiment, right? I mean, we can't randomly assign one group of people to smoke cigarettes for 20 years and another group not to. That would be completely unethical. So for questions like these, researchers have to pull out a different set of tools.
And this is where observational studies come into play. Instead of setting up an experiment, researchers act more like detectives. They just observe. They watch people in the real world, digging through existing data, like medical records, looking for patterns. These studies are awesome for looking at long-term effects, but because there's no randomization, that risk of a hidden confounding variable, remember our summer heat example, is way, way higher.
So if we put them side by side, the difference is crystal clear. In an RCT, the researcher is active. They're assigning the treatment. In an observational study, they're passive. They just watch. And it's that randomization in RCTs that makes them the gold standard. They give us really strong evidence for causation. Observational studies, on the other hand, can usually only suggest a strong connection, an association.
Okay, so why have we been geeking out about all this? Because understanding this difference isn't just an academic exercise. It's absolutely central to the field of biostatistics, and it has a huge impact on what might be the most important thing in our lives, our health.
Literally every single time a new drug gets approved, or a new vaccine is rolled out, or you see a new public health guideline, it's because biostatisticians have used these exact methods, RCTs and observational studies, to wade through mountains of messy data and pull out clear, life-saving decisions.
And the stakes here are just unbelievably high. Get this, over 90% of drugs that look promising in a lab and then enter human clinical trials ultimately fail. They either don't work or they're not safe. That's why these methods are so critical. They are the firewall that protects all of us, making sure only the safest, most effective treatments actually make it to the pharmacy.
And this kind of thinking is everywhere. Yeah, it's the bedrock for developing new medicines, but it's also how we figure out if public health policies, like smoking bans, are actually working. It's how we untangle our risk for diseases, and it's even paving the way for treatments that are personalized just for you.
So the next time you see one of those headlines that says, drinking this tea cures everything, or eating that superfood makes you live to 150, you can stop and think like a biostatistician. You'll have the tools to ask, wait a minute, is this just a correlation? Or is there real causal proof behind it?
And that's our deep dive into cause versus correlation. If this helped you see the world of data a little more clearly, do us a favor and hit that like and subscribe button for more explainers. And seriously, we want to know what we should tackle next. Drop a comment below and let us know what topic you want us to break down. Thanks so much for watching.